Thank you so much to everybody coming here today. It's really an honor to present this work here for you today. And it's also an honor to have done this at Linköping University. That has been the home for me for many, many years. And I would also like to point out that Anders Haraldsson is in the audience here, who was the person who introduced functional programming to me once. And that kind of thinking has been very influential when I found functional psychology that I will speak a lot about today. And I think Anders also represents this AI group that moved from Uppsala in the early 70s to Linköping. That this work, so to speak, is some kind of, I don't know, continuation on. So thank you very much, everybody, for coming here today. And I will speak about the work I have done by introducing the topic of artificial general intelligence, learning psychology, Nars, and then explaining, as Björn asked for, what machine psychology is. And I will mention my empirical studies and some conclusion. So artificial general intelligence is the task of creating general purpose computer systems, which really is something else than creating these special purpose systems that we hear a lot about. These systems that can do game playing, classify images, text-to-speech synthesis, and so on. And this question, many people say this is the original goal of AI. Other people like Margaret Bowden has called this the holy grail of AI research. So of course, this is an extremely difficult problem with many different approaches. And since about 2008, it is a distinct research field within the AI community with its own journal community and annual conferences. So one way to say it is that the work I present here today is part of that AGI community. And there are different approaches, of course, then to this question. Is it possible to close the door up there? Thank you very much. So maybe it's closed. Thank you, Peter. So to quote Christian Balkenius, one approach to AGI is to do a faithful reproduction of known brain processes in a system-level model that incorporates a large number of components modeled after the human brain. So an approach that many people think about is basically to copying the human brain into a computer. That's one approach to AGI. Another approach that many people are familiar with these days is to do as ChatGPT does, like trying to mimic human behavior as close as possible, for example, in conversation. So that's another approach. Another approach is to identify and implement a single unifying principle. For example, the principle of adaptation within sufficient knowledge and resources, as suggested by Pei Wang with his Nars model, that this work follows. So we have used the Nars model in this work. This is Chris Torreson, a professor at Reykjavik University. He wrote, together with others, the preface for the latest proceedings from the AGI conference. And he wrote like this: but the biggest contribution to scientific knowledge that AI could provide is a comprehensive theory of intelligence. No real progress can be made without it. So then the question is how to find a good AGI theory. And the approach I have taken to this is from the perspective of learning psychology, that I will explain now what that is. So very much that I present here is based on the work done by Jan de Houwer to the right, described, for example, in his book here, The Psychology of Learning, on MIT Press. So learning psychology, as described by Jan de Houwer, is the science of ontogenetic adaptation, so adaptation that is during the organism's lifetime. It originates from the work by Skinner, but I would say it's very much clarified by Jan de Houwer and his colleagues. And Jan defines learning as a change in behavior that is due to regularities in the environment. And this is something that uses functional relations. So Ernst Mach was a philosopher that suggested the use of functional relations, describing relations between independent variables and dependent variables. So for example, in this case, describing the relation between regularities in the environment and behavior change. So functional learning psychology really defines learning as an effect described as a relation. Learning in this kind of psychology is an effect rather than a mechanism. So principles such as operant conditioning that most people here have heard about is something that can be described as an effect. So here is an example of operant conditioning that I hope we can hear the sound. It's a dog. You can see the dog here. It's me who have trained the dog. So this is a change in behavior. You can say the howling, ylandet. That is due to the fact that we have given the dog food after the sound in the context of me sounding like a horn. So this effect is something that can be described as operant conditioning. Another way to say it is that it's the impact of the sound of a horn and food, that's regularities, on behavior change. So once again, functional learning psychology explains behavior change due to these regularities. An alternative way to talk about learning psychology is what can be called cognitive or mechanistic learning psychology, that really aims to explain what are the mechanisms underlying this type of learning. For example, what happens in the brain, what happens in some kind of associative structure or some kind of propositional network. That's another type of explanation. So these two are really complementary. So this type of learning can be called standard learning or simple learning, or operant conditioning. Complex learning is one step more advanced. So here, for example, is a sea lion that has been trained to always it sees something in the middle and pick the same object. So it acts on the identity relation. Even if it hasn't seen these objects before, it knows that it should act on pick the identical one. Here is another example, a dog who has been trained to always pick the largest object or the largest circle. So these two examples are once again something that can be called complex learning, that is given Jan de Houwer's framework, called the joint impact of multiple regularities. It's also called the effects of meta-regularities. So all of these are something that animals can do. So then the question is, how about human level intelligence from this perspective? And I would say that no one has done more to this than Stephen Hayes, who in 1982 had an insight after thinking about this for 6 years. And the insight he had was, maybe relating is an operant. So that means maybe the fact that we do relating in an arbitrary way, maybe that in itself is operant behavior. Maybe that is something that is learned throughout the lifetime. Maybe a lot of the cognitive thinking we do is actually learned behavior. So this is the title of a paper from 2021 relating is an operant, a flyover 35 years of RFT research. So here's an example of this type of learning. So for example, let's say that I ask someone to pick either B1 or B2 in the context of A1, and someone picks B1. Okay, so after that, I present this. What to pick if B1 is on the top? Should I pick A1 or A2? And this can be totally trivial for a human being, but this is actually something that almost no non-human animal can do. So here's how to explain it. So once again, let's say that this is how it's explained from the perspective of relational frame theory, the theory that Stephen Hayes has created about this. So let's say that someone is trained on picking B1 in the context of A1 and then tested on the reverse. Relational frame theory suggests that a history of multiple exemplar training is needed. So let's say that we have been trained in the seeing the pattern both ways, so to speak, before this. So in the context of X1, I pick Y1, and then also with feedback, I pick X1 in the context of Y1 on the top line there. And being able to abstract a symmetrical relation from that I can use in a new situation. That is the thesis by relational frame theory, that this type of relating is learned, and that this is the smallest step of advanced cognition that only human beings can do, and they can do it already at 16 months of old age. So relational frame theory is a theory about something called arbitrarily applicable relational responding. This is learning these types of arbitrary relations. So intelligence in itself, from the perspective of RFT, is these complex combinations of arbitrary applicable relational responding. So from this perspective, intelligence is learned behavior from this perspective of relational frame theory. But then the question is, can RFT be a theory of AGI? So how to qualify a good theory of AGI? This is according to Pei Wang. He suggests that the theory of AGI needs to be correct, compact, and concrete. That means, in this case, relational frame theory is correct in the sense that it's backed up by very much experimental evidence. It's compact, it's a very coherent, parsimonious theory. But it's not concrete in the sense that it cannot be implemented in a computer directly. So how to deal with this, that RFT is not concrete? That's the idea of this thesis, that we use this system called non-axiomatic reasoning system to implement the principle from learning psychology and RFT. So just to highlight the compatibility here, that in learning psychology, learning is defined as ontogenetic adaptation, and in Nars, intelligence is defined as adaptation with insufficient knowledge and resources. Another way to say it is that Nars is what can be called a principal AI, in that it seeks to implement a single principle, which matches perfectly with the functional learning psychology approach that really seeks to understand principles like operant conditioning. So it's a deep compatibility here. So what is Nars, the non-axiomatic reasoning system? So it's described here, for example, in this book by Pei Wang from 2013. And Pei has worked with this since the 1980s. And Pei Wang, Nars, the system implements his so-called non-axiomatic logic. And Nars in itself, it's a reasoning system. And it's designed to be adaptive in the sense of that it operates with insufficient knowledge and resources. And if it's anything that I think that Pei Wang should receive the Turing Award for, it is this principle of the assumption of insufficient knowledge and resources. That's the first design principle in Nars. Everything in the design comes from that. It's designed as a term logic, which in a way is a very unusual logic. And at each cycle of the system applies logic rules and derives conclusions. And these, I'm looking at Peter Johansson, professor in complexity theory. All of these applications of logic rules are done in constant time at each cycle. And the reasoning process can stop there after 1 or 2 or 3 cycles or go on forever. So one way to say it is that the non-axiomatic reasoning process, the problem-solving process, it's a non-computational process implemented in a computer. So at each step, it is computation. But the problem-solving observed by Nars is something that is not computational. Nars has frequency and confidence as its dual truth values, which enables it to deal with both positive and negative evidence at the same time. And a very important thing comparing Nars to a lot of other AI systems is that it's not pre-trained. So it's not data-driven in that sense. It's pre-trained in that it has its fixed mechanisms and it learns in interaction with the environment as an animal or human being. It has something called experience-grounded semantics. So the meaning of a symbol in Nars is something that comes from experience. Another way to say it is that the root metaphor of Nars is neither computation nor a dynamical system. It's more of a self-organizing process. So in a way, Nars is different from both from symbolic AI and machine learning. And this work uses a particular implementation of Nars made by my 2 colleagues, Patrick Hammer and Tony Lofthouse. Here is we in Stockholm a few months ago. It was still warm outside. And this is the result of Patrick's PhD thesis. It's an extremely effective implementation done in the language C that was designed to be used with robotics application. It's really, really fascinating because it's designed for sensory motor reasoning, like animal learning at the core. So it's immediately a very strong compatibility with learning psychology there. It makes use of Tony Lofthouse event-driven control mechanism called ALAN. That is a totally different way of dealing with control in Nars. I didn't say that, but every Nars system can be described by having a logic part with logic rules and a control mechanisms that deal with how to combine logic statements. So Tony's control mechanism does it in a very in a new way compared to previous systems. And another very fascinating thing is that Nars can reason on streams that are provided by other systems like object classifiers. So for example, if we have some kind of image classifier, Nars can reason on the terms that comes out from that. And also related to this work is that at compile time, we can define what components of Nars, what mechanisms are there. So we can really build exactly the pieces that we want in the Nars system. So what do I mean with machine psychology? So it is really the aim is to integrate functional learning psychology with Nars, and meaning that we take principles from learning psychology and implement it with a principal AI system. I assume Christian, in his own PhD thesis, implemented like conditioning based on brain-based mechanisms. Here we implement that with a reasoning system. So it's really what I have done is what I would say a bottom-up investigation using the open Nars for applications, the sensory motor part of that. And we then are able to use methods and from learning psychology, and also relational frame theory, which is a learning psychology theory. And one way to say it is that Nars takes the role of an organism in our experiments. So it's really like we do the kind of experiments we have done with an animal or a human being, but with Nars instead. So Nars is the participant in that sense. And what I would like to highlight is also that it becomes a very nice scientific approach, I think, that we can manipulate the system's experience as with any animal, but we can also manipulate the system's mechanism. So at the same time, those two are independent variables, where I would say that adaptation with insufficient knowledge and resources is the dependent variable. So the goal of this is then a theory-driven, interdisciplinary approach to artificial general intelligence. So what does it look like when we interact with Nars? We can imagine that we have Nars running on a robot like this. This is one of the robots that is possible in Stockholm to buy in Åkersberga, imported from China. And if we assume that this is what the robot sees, then we can encode this as something that we would like. For example, if we want to use a psychological procedure called matching to sample, we can decide that the sample is in the middle. And the choice options of left and right is something that also is in the visual field like this. So this is something simply defined as locations. So this looks a bit abstract, but this is how we would describe a situation where we have something green to the left and something blue to the right. So what this means is that it's an interaction between location and color in this sense. So at the same time, it's an event of seeing something green to the left, which is then, yeah, like that, and also seeing something blue to the right. It doesn't have to be encoded like this. This is an encoding that we invented earlier this year, but it solves other problems of showing this to Nars. And the colon/ there, colon at the end, is to describe it as an event in time to the system. So this is simply presenting two events in time to the system. We can also describe more complex objects like this, like a red triangle in the sample position, or a blue square, or a green circle. And once again, thanks to Patrick and Tony's brilliance, it's possible to also use some kind of object classifier as events to the system. So we can take that as the eyes of the system to, for example, see a cat at the sample and bird to the left and dog to the right. And also at the same time as that, detect colors. So in this case, the system would have two types of eyes, object classifier and color detector. So the empirical studies. So one way to say the purpose of these empirical studies is to validate this framework of machine psychology. So then we start from the bottom with operant conditioning. And what I would like to highlight here is that at the very first level, the very, very basics, we study operant conditioning as the simplest form of ontogenetic adaptation in this system. You can call it standard learning, as I say. And the only mechanisms that we have kept in the system, in the Nars system, is those two that are called temporal and procedural reasoning. In Pei's book, they are described at various layers. So anyone familiar with that? These are only layers 7 and 8. So the first research I describe is done on an organism designed to only have these abilities. So 3 experiments. And once again, this is not pre-trained in any way. We just start up Nars with some kind of, some init code. So let's say that the task is to always pick green, independent of location. We use an experimental design from learning psychology, baseline training testing. And it looks like this when we show it to Nars. First the 2 events, left green, right blue. Then it says G exclamation mark. That means that G is a goal that the system wants to achieve. The system has no knowledge at this far, so it has to rely on something called motor babbling. It just does something. It babbles left, which happened to be right. It was correct. So we provide G as a consequence. We as researchers provide G as a consequence. So then, using the mechanism of temporal induction, only from this single experience, Nars forms this weak hypothesis. Maybe it is a pattern like this. When I see something green to the left, I should select left. That would lead to G. That's a one-shot learning, and it's an inductive mechanism. And it can learn the same for both left and right, like this. Then, in a later situation, the system sees the same situation. The right to the blue to the left and green to the right. So it's shown like this, and the system once again has G exclamation mark. So what here it knows from before this knowledge that we talked about. So it can use the mechanism of goal deduction to derive that, I should probably select right to achieve G. So it's 2 different mechanisms, temporal induction and goal deduction. Then we can use the experimental design like this to demonstrate that in the baseline, where we don't give any feedback, the system doesn't learn anything. During training, it does learn. And in testing, once again, without feedback, it demonstrates what it has learned itself. And the green line describes the increase in confidence in this hypothesis. So once again, one slightly more advanced attempt.
Can you hear me now, Patrick?
Oh, yes.
Yes.
Thank you for saying that. So anyway, this is an illustration of when the system readapts. So it first learns the green hypothesis, so to speak, then the blue one. This is one step more advanced. Here is another example of, you could call it conditional relations. So for example, if the system learns to pick blue in the context of green, or pick yellow in the context of red. So this is something that can be called conditional discriminations. And once again, this is something that Nars can learn by extending the length of the hypothesis one step more. So I would argue that this is the very, very most simplest form of what can be called a relation in that sense. This is an if-then relation. If green, pick blue, for example. So this is animal level if-then relations. So conclusion of this is that Nars can learn in the form of operant conditioning, and it uses, then we have demonstrated that temporal induction and goal deduction is necessary and sufficient. So this is really a demonstration, I would say, of ontogenetic adaptation. So the core of what I mean with machine psychology is really about this. So it's really possible to do this kind of research where we show which mechanisms are necessary and sufficient. Okay, one step more advanced, generalized identity matching. This is something that Jan de Houwer, this is what the sea lion did on the picture. Jan de Houwer would call this complex learning. And you see it says plus abstraction. So it means that we use the mechanisms from before, but we add one more mechanism called abstraction. And so this is an example of such task. If the system is trained with feedback that in the context of green, I pick green, in the context of blue, I pick blue, how will the system act with new colors that it has not seen before? So this is something that the system can once again be trained in like this. And in addition to learning the same hypothesis, similar format as before, the system also learns this kind of abstract version of it by introducing variables. So seeing a more general pattern, and it's that general hypothesis that it can use to solve new situations. So the blue line there represents the increase in confidence value for this general hypothesis. So that means that during baseline, it doesn't get any feedback. During training, it gets feedback. On the identity test, it tests on the old colors. And on the last phase, the generalized identity test, it tested on colors that it has not seen before. So it has to rely on the abstract hypothesis. This is something we have been playing around with more recently. I don't know if you can see it, but these are different shades, different levels of brightness. So it's supposed to be other brightnesses on the far right there. So this is another type of abstraction that's called comparative reasoning. So it simply means that Nars, if we encode the situation in another way, Nars can derive something like this, that if the sample and left are equally bright, then I match the sample and left, for example. So it's another type of abstraction. So conclusion here is that Nars can learn in the form of identity matching, generalized identity matching, a more advanced form of ontogenetic adaptation, what Jan de Houwer called complex learning, an effect of meta-regularities. And we can show that we can use either abstraction in the form of introducing variables or abstraction in the form of comparative reasoning to achieve this effect. Functional equivalence. Here is you didn't ask me, Björn, if I wanted to change something in the thesis. And I forgot to say that 10 minutes before I was about to submit the final proof, not the thesis, the final proof, I had an insight that the structure of the thesis could have been done differently. So what I call functional equivalence as a mechanisms, I would prefer to call it implications in two ways. An equivalence is implications in two ways. Sorry for not clarifying. Anyway, the mechanism that we have been introducing here at this layer is implications to study complex learning in the form of functional equivalence. Here is an extremely basic version of this. Let's say that the system is trained that in some context A, I do an operation that leads to G. And then later, in the context of B, I do the same operation leading to the same consequence. Then if the system acts on both these contingencies, the system can derive an equivalence between A and B. So if the operations are the same and the consequences are the same, the system derives some kind of equivalence between A and B, functional equivalence, even if they don't share any properties. And this is something we describe with these two-way implications. And one way to study this is to replicate a study by Paul Smith, Dermot Barnes, and Brian Roche, that they studied this with children. And here's how they did it and how we adapted it. So if the system is trained, so R1 and R2, that's operations, that's responses, pressing R1 or pressing R2. So if the system in the context of A1 in the middle and B1 in the middle are trained to do the same operation, we expect the system to derive some equivalence between A1 and B1, and the same for A2 and B2. And if we then retrain the system, so it's the same context, A1 and A2, but the system is trained in a new operation, can the system then use these new operations in situations that are functionally equivalent? So this is basically the task they gave to the children, and Nars can do this with this mechanism. So it derives something like this. A1 and B1 are equivalent in this context. Okay, so now back to the smallest step of abilities that only human beings can do. Maybe one or two sea lions, maybe a pigeon under very specific circumstances. Do you remember this? That A1 and B1, that the symmetrical relation is trained by this previous experience of seeing it both ways. And this is something that we have demonstrated by using functional equivalence. I would call it a higher order functional equivalence. And I won't go into the details of this, but this is actually quite fascinating. That we can actually show this ability with mechanisms that are only available in the animal kingdom, so to speak. Maybe that could explain why some extremely smart animals could do this under highly specific conditions. But it's not in the, it's something else than what Steve Hayes was talking about. Or actually, this has been debated since the 80s. What is the difference between these types of relations? So anyway, functional equivalence is something that we have demonstrated with Nars. It's what Jan de Houwer called also complex learning in the form of moderated learning. And the mechanisms we used we added on top of the others is implications. So a form of symmetry was also enabled. So the final part of this, that is also the most, I think, exciting and most difficult and most work in progress, is how to deal with arbitrarily applicable relational responding. That's really human level intelligence. And the idea we have been working with since about February 2023 is that we use something called acquired relations in addition to the previous mechanisms. And this is a bit abstract, but I will say something about it. So this is Pei Wang's book, and in chapter 8 on relational terms, he has this formula. It's basically a mechanism to reduce and combine statements into relations. And this was really a breakthrough in our research to find this, or to understand whether we can use it in this context. So here's the idea about this. And if it's anything that I think can be very, very, well, how to say it? Oh, I describe it in another way. Do you remember that I said that picking blue in the context of green can be seen as an animal type of if-then relation? So we have previously demonstrated that the system can learn a simple hypothesis or contingency like this. When green is the sample and blue to the left, I match sample and left. That's animal type of learning. But here is the suggested idea that if the system at this stage thinks about this more as relating, the system acquires relations. It introduces a green and blue relation here of the type color, and also a sample left relation. Then we could describe something like this, and this looks horribly abstract, but it basically means that we can ground the relations of relating color and location. We can ground those in the contingency. So this basically means that a symbolic relation, its interpretation is in the animal level learning, so to speak. And this is extremely abstract idea, of course, but it's one way to start forming symbolic relations bottom up from experience. And we can also introduce variables like that. So it can be used across situations. And I will now describe the same problem with symmetry, but using these other mechanisms. So let's say that the system learns to pick y1 in the context of a1. It would then, according to this mechanism, acquire two relations, the xy relation and the sample left relation. It would then introduce this implication that we ground the conjunction of these two relations in the animal level contingency. So it's really the meaning of that relation is this type of acting in the world. And we can introduce variables. We can learn it the same for the picking x1 in the context of y1, the reversed version. And we could then represent this symmetry as an equivalence between these two relations. So it's a much more compressed representation of symmetry. And the same idea goes across for much more advanced, so transitivity, for example, can be described like this too. So then again, the system remember, it has been trained on X1 and Y1, Y1, X1, comes to the situation and learns that A1 and B1, they are related, but it could then derive using symmetry that B1 and A1 should also be related. And here is what I would call the weak part of the argument, that to be able then for this to work is that the system in some way needs to acquire a relation sample left location from interacting with the procedure. So it's basically some kind of sensory motor interaction that triggers the system to acquire that. Because if that is also acquired, it can use this previous abstract knowledge, put that into place, and remember, this is a situation that the system has not seen before, and derive animal level relation, so to speak, that it can act on, and then press sample left here. So I have also in the thesis explained how much a step more complex relations can be reproduced. I won't go into the details here. A more, let's call it, this is something that you could expect maybe a 5-year-old to do. How we can explain that using this mechanism, and a much more advanced experiment with same and opposite relations. So conclusion here is that it seems that Nars and the logic there is capable of describing the development of arbitrarily applicable relational responding. And this is definitely a human level only form of complex learning. And the mechanism that we suggest is acquired relations. And just to be clear that if this would work and the control mechanism could handle it, it would mean that the same mechanisms could be used to learn any type of relation like this. So a lot of, let's call it, different type of cognitive tasks could be used with the same mechanisms. So I personally think that if this would work, it would almost be like, I don't know how to describe it, really adult human level intelligence. And of course, there's lots of challenges left there. So conclusion here. So as many people suggest, including the preface written by Chris Torrison and others, the AGI field needs theory-driven research. Learning psychology and relational frame theory seems to provide helpful theories. And Nars in general and open Nars for applications in particular seems like very promising candidates for implementing these principles from functional learning psychology and RFT. So machine psychology, as I describe it, is this interdisciplinary framework where we integrate functional learning psychology with Nars. So I would say that with machine psychology, it is possible to do theory-driven AGI research. And the empirical studies that I have presented here is one way to start validating this framework. So exciting future ahead. Thank you very much.